Welcome back. After discussing the general concept of photovoltaics and the role of PV in the energy transition in the first part of this MOOC, and after discussing the various PV technologies in the second part of this MOOC, we now are going to discuss photovoltaics on the system level. The learning objective of this video lecture is to get familiarized with a wide variety of PV systems. Generally speaking, we can divide the PV systems into two main groups. On the right hand side are the grid connected systems, and on the left hand side are the stand-alone systems. Let's start by looking at stand-alone systems, which are also known as off-grid PV systems, to differentiate them from the grid connected group. As we will see over the next couple of slides, the first two subgroups rely only on solar power. These subgroups can include energy storage such as batteries. The third subgroup instead is a hybrid system where the PV production is coupled either with wind turbines or with a diesel generator. Let's go through these configurations one by one. The most simple PV system is the direct current PV system without storage. Here, the DC output of the module or array is directly connected to the DC load. A practical example is this toy that embeds a small solar panel, which is highlighted in red here. It is also possible to connect AC load in this simple PV system without storage. Connecting an AC load involves adding an inverter, which converts DC to AC power between the power source and the load. Then we have DC systems with storage, with a somewhat more complicated topology. The charge controller is connected on one end with the storage unit and the other end with the PV modules. Indeed, when batteries are implemented as a storage system, a charge controller is required. It has the task to disconnect the batteries from the PV modules when the batteries are fully charged, and may disconnect the load to prevent the batteries from being discharged below a certain limit. A DC system with storage is widely used to charge smartphone batteries with solar energy. It is also used in the Nuna car series, the racing car designed by TU Delft and powered only by the sun, which won several editions of the World Solar Race in Australia. Then, with a slight modification to the system, AC loads can be powered by adding an inverter. This is the case of buildings that are completely independent from the grid. Note that in most modern houses, DC power is supplied directly to all the DC appliances without passing through an inverter, which would waste a lot of energy in the conversion. In addition, the batteries in these types of systems must have enough capacity to deal with the day-night mismatch between generation and consumption. Moreover, these domestic battery systems must also have enough capacity to face long periods of low radiation intensity due to weather conditions. An example of this system is the design of innovative hotels or concept buildings. These buildings use all kinds of renewable energy technologies such as wind, tidal and solar energy. The structure might contain a DC microgrid in case the owner wants to use only DC loads. For example, televisions that are directly working in DC. Then, if needed, the building can also have a connection to the grid. The bottom line is that the system can become more or less complex, depending on the final applications. To conclude the stand-alone group, we have hybrid systems that combine PV modules with a complementary method of electricity generation such as diesel and or wind generation. You can imagine to back up your energy supply and reduce the generation consumption mismatch of solar power by introducing an alternative form of power generation. To optimize the different methods of electricity generations, hybrid systems typically require more sophisticated controls than standalone or grid-connected PV systems. For example, in case of a PV diesel system, the diesel engine must be activated when the battery reaches a given discharge level and stopped when an adequate charging state is reached. Therefore, the diesel generator works as a backup, which can be used to recharge batteries or to supply directly the load. In case of wind and solar, this combination has the advantage that the two sources complement each other because the peak operating times of each system occurs at different times during the day. The power generation of such a hybrid system is more constant and shows less fluctuations compared to the subsystems individually. On a normal day with the sun out, the PV modules on top of this rooftop are busy converting the incoming irradiance into photo-generated power. The battery is constantly being charged or discharged through the charge controller depending on the different PV supply and load demand. The off-grid or standalone inverter is continuously converting the DC power to AC and supplying this AC power to the loads. The system is designed and sized such that during the day, with the sun shining, the system generates enough power to at least meet the load demand for the rest of the day. Therefore, the PV system acts such that the battery is net charged over the day. After daylight, the rest of the power demand is fulfilled by the battery. Let's now move to the second group of PV systems, the grid-connected ones. Grid-connected systems are typically used in buildings. They can be connected to the grid directly or via a household and might also include storage, as we shall see in the next slides. In the simplest version, PV modules are directly connected to the grid via an inverter, which converts the DC power coming from the modules into AC power for the grid at 230 volts and 50 Hz in Europe, for example. In case of small systems such as those installed in households, the inverter is connected to the distribution board. This device has the role to transfer the generated power into the electricity grid or to the AC appliances in the house. In this way, the grid acts as a buffer into which an oversupply of PV electricity is transported and redirected to other loads. Indeed, these systems do not require batteries and the grid supplies the house with electricity in times of insufficient PV power generation. Nowadays, however, more and more residential systems have the possibility to store energy, for example, in batteries. As a consequence, also the charge controller is required. This layout is very similar to that of a standalone system, but it has higher reliability thanks to the connection with the grid. Moreover, batteries can be programmed to store electricity from the grid during the night when the price is lower and then use it when the PV generation is insufficient. Another way to classify PV systems is by installed peak power. Here we have some pictures of different kinds of PV systems. In the first row, we have a class of systems called rural or standalone systems with eventually a local grid. In this case, the rated power is quite low, between 10 watt peaks up to 10 kilowatt peaks. Going up in power, there are grid-connected building integrated systems. These can be found, for example, on the facade of a skyscraper, on the rooftop of a residential buildings and train stations. This topology is easily scalable from very small systems in the range of 1 kilowatt peak to megawatt peak scale installations. Finally, we have power plants with a peak power of several megawatts. Solar power plants are connected to the electricity grid via three-phase inverters. In this last slide, we classify various PV systems according to their function. We start with two main categories of PV systems that occur when photovoltaics are either added onto buildings or integrated into buildings. On the right hand side we have the build-added photovoltaics, or BAPV, which refer to photovoltaic systems laid down onto the building after its construction of the building is completed. On the left hand side we have building integrated photovoltaics, or BIPV, in which PV modules replace conventional building materials. These two categories can not currently define all the innovative applications involving solar energy and the environment where we live. Therefore, the concept of environment integrated photovoltaics, or EIPV, includes BAPV and BIPV and much more. We have, for example, bicycle roads realized with solar modules, alongside charging stations for electric bicycles, colored pergoglass for e-parking lots, and off-grid info points that provide you with relevant information and has the possibility to charge smartphones and tablets. As a recap, we have categorized PV systems first by its role and function in the bigger energy system. The standalone PV system without storage, with storage, and hybrid system at one side, and the grid-connected PV systems like directly via household and with storage-powered PV systems. A second classification of PV system discussed is classification by installed peak power, going from rural standalone PV systems to large-scale utility PV plants. The type of PV system determines which components needs to be integrated in the system. What are all the components in a PV system? We will discuss that in the next video. So see you in the next video.